Okay, so bottom line is, instead of talking about individual galaxies, we're going to be looking at galaxies and clusters for a few minutes. So just a quick overview, clusters and cluster findings, sort of the general introduction. The next 2 points are the things that I've been looking at specifically, which is the conditional luminosity function of red galaxies and clusters, and the distribution, the spatial distribution of galaxies and clusters, and finally I'll comment on what we're getting from our results and what we expect to do in the future. So a quick reminder of why we care. So clusters are obviously the best place to look to try and understand the effect of a high density environment on galaxies. This is, your galaxy gets accreted, it goes from star forming to red and dead. How do accretion and destruction of galaxies and clusters relate? How does this change with cluster size or with redshift? And how is stripping different for galaxies at different radii? These are all things that you have to look at clusters to try and understand. And finally, in the long run, in a slightly different tangent, understanding the details of clusters and the galaxies in them is very useful for trying to understand cosmology, since these massive structures are very useful tracers in understanding dark matter. Okay. So a note on how we're finding our clusters. These are not X-ray selected or SC selected. These are optically determined clusters. They are found using RedMapper. So this is the new Red Galaxy Cluster Finder that's out in a couple of papers at the moment. There's Rykoff et al. 2013 is the one I have a picture from here. It essentially uses a color filter to select red galaxies which are spatially related into clumps. It uses all the galaxies in a cluster to estimate a redshift, which is what you're seeing here in this plot. It's showing, in the scatter plot, it shows the estimated cluster redshift using all the galaxies along the x-axis, and the y-axis is a spectroscopic redshift of a cluster member. It is particularly useful since it includes membership probabilities, so you might have a 50-50 shot of a galaxy being in a cluster. It gives an appropriate weight for that. It also includes appropriate weighting for galaxy centering. Maybe you're not sure which galaxy is the center of your cluster, and also a P of Z, giving you the essentially the probability of your cluster being at any given redshift, which is really useful. The other major important point, which is particularly useful for analysis, is that there's a pretty low scatter in the mass to richness relationship, which has been measured compared against X-ray and SC measurements. Okay. So, various data selections I'm going to be showing you pretty pictures of in a moment. We draw from DR8, which is about 10,000 degrees. There's way too many clusters in here. It's complete in the sense that it has essentially volume limited to our chosen luminosity threshold to about 0.35, stripe 82, much lower area, much greater depth. Ultimately, we plan on applying this to the dark energy survey, which has the delightful combination of large area and very high depth. So this should be very useful in the long run for doing evolution to relatively high redshift. Just so you know how many things we're looking at, this is the density of clusters in our sample. The nice thick black line is DR8. The other two are the high and low redshift chunks of our stripe 82 selection. This lambda along the bottom is our richness estimate, which is the weighted sum of the number of red galaxies in our clusters. So the first thing is the conditional luminosity function. So this is, if you were doing it in a simulation, it would be bins in mass, and then the distribution of the luminosities of all your galaxies in that bin. So it's the luminosity function conditioned upon the mass. Here it's actually a richness range. So in this particular case, this is a richness range which is roughly equivalent to a bit below 10 to the 14. So this, the bottom line to draw from this is that you can see very, very nicely the two different parts of the distribution. The first is the Schechter function in black, which is the distribution of satellite galaxies. You can also see in the blue the BCG, the central galaxy of the cluster, and these are clearly distinct. And for bonus points, the lines that you see are a single fitting function across all redshift and richness bins. So there's some simple relationships involving power laws between essentially the parameters of the Schechter and the log normal function for the essentials. And so far, it's essentially the data is beautiful. And from this, we can look at the, essentially move from this to looking at the evolution that we've measured from our fits. So big plot, bottom line is that you see all of these lines up here, all the different lines are all of the fits to all of the redshift bins in all of the richness bins all at once. And for the most part, our evolution is consistent with essentially a certain amount of passive evolution. We don't see any extreme strange things going on. It's really very simple, and we're looking into this further at the current time. And just to show you the higher redshift version of this in this stripe 82, we have fewer richness bins here because there's a lot fewer clusters to look at. But essentially the same is true, and the two fits are consistent with each other. Okay. So tagline, if you want to also look at the radial distribution of galaxies and clusters, we can do that also using this data. In terms of evolution, there's a lot of lines and a lot of points on these plots. The lines are fits using a projected NFW profile to the number density of galaxies as a function of radius in your cluster. And what we find is that these are all consistent with projected NFW profiles. And as you can see from the fact that everything is basically on top of each other, it's also pretty consistent with not very much redshift evolution.
What kind of concentration you get?
So we haven't measured concentrations directly since we don't have virial radii, we don't have halo information directly yet at this point. We do have scale radii, which are in the neighborhood of 150 to 200 kiloparsecs. So which is not too far off from what you'd estimate for the scale radius of a dark matter halo of roughly the right mass. Okay. So the other thing to note is that for the data that we currently have, we're not seeing a lot of extra stripping at the center. Which is sort of interesting. We don't see a flattening or sharpening. We don't see any unusual features that you might expect near the center of the halos where you would think that the BCG might have some additional effect. Okay. And in case you want to see what the stripe 82 looks like, the data is a lot noisier, but the results are pretty similar. So just to summarize, we have the bottom line that as you go to higher redshift, the conditional luminosity function brightens as you would expect, mostly similar to passive evolution. Something else to note is that the satellite conditional luminosity function, that brightness is essentially constant with richness. L star doesn't change as a function of your richness measurement. The radial profiles are essentially consistent with NFW, and we look forward to repeating this on the early DES data that is already available to full depth and ultimately to the full survey. That's all I have.
All right. All right, questions? Hojo.
So you use red sequence galaxies to define your clusters, is that right?
Right.
So then the question is that if you change your criteria, will that change the result? Because, and also you want to look at evolution. But if you say the color changes as a function of redshift, then you use your that kind of identification. If there were evolution, where you be able to, just use this kind of selection, where you be able to see it all.
So I think we would probably still be able to see it, particularly since the cluster finder is tuned to essentially define the red sequence as a function of redshift. So maybe you could come up with something that would get hidden by the cluster finder, but at this point, we're not currently seeing something like that, to my knowledge.
Actually, identifying those peaks is very insensitive to how you define the red sequence.
Yeah.
Other questions? Joel.
Could the same type of experiment be done for field galaxies? And if so, has it been done?
So I think it's kind of hard you can't really use a red mapper result on field galaxies just because the red mapper redshifts are based on using clumps of. So yeah, there's definitely been work done using the conditional luminosity function on field galaxies. There's some Yangmo and Vanden Bosch papers that have done some work, and there's some other work that I've done on low redshift field galaxies.
Have you compared the two between cluster and field?
We haven't done the direct comparison at this point, and it's going to be a little bit tricky just because the conditional luminosity functions here have a color selection.
Good, that's for the future. All right, let's thank Rachel again for your presentation.